Welcome back to Algorithms and Uncertainty. In the last lecture, we introduced algorithms for fractional ski rental and the fractional version of online set cover. We derived them in a complicated way, or at least somewhat complicated way, via the primal dual framework. Today we'll ask the question of how to get integral solutions. We'll do this in a randomized way, so that eventually we will end up with a better randomized algorithm for ski rental, and also with finally a randomized algorithm for online set cover. Before we do this, let's once again recap where we stand. So we devised algorithms to solve such LPs online, which are that we want to minimize the cost of our cover, subject to the constraint that each element in our universe is covered by at least one. And the way we have to do this online is we get to see one of these constraints at a time. Only when we get to see the constraint, so we get to see an element, we then get to know how we can, in principle, cover this element, and then we have to maybe increase the variables so that this element is indeed also covered. And as I was saying, we derived algorithms for this. One algorithm for the special case of the ski rental version of this LP, and one algorithm which has a worse competitive ratio for the general form of this of this optimization problem. And today we'll ask the question, how can we obtain integral solutions? Which means that we still want a solution to this, and actually everything is the same except for the fact that these x-axes should be either 0 or 1 at all times. And the way we will do this is we will kind of interpret them as probabilities and then do randomized rounding, although things are not as easy as in some other settings, in offline settings where you can just easily do randomized rounding. Here, of course, we have the difficulty that we do not know in advance the entire solution. We don't know in advance the entire LP. But fortunately for us, we do not actually have to look at what these algorithms that we obtained last time, what they actually do. So all this primal dual business we can ignore for today. We just take some black box algorithm for these fractional problems and add some randomization on the outside to then derive integral solutions. And to get started, let's first consider the ski rental problem. So our LP relaxation is still the following. We want to minimize b times x by plus the sum of the x rand t. And what are the constraints? We'll have to cover each day, and of course variables are non-negative. And what we derived last time was an e over e minus 1 competitive algorithm for the fractional problem. So what might this look like? If, for example, the cost of buying the skis is 3, then on the first day we would set the buy variable to 4/19. On the second day we would set it to 10/19, and then on the third day we would set it to 1. And this we analyzed last time, so we don't have to care about really where this sequence is coming from today. This is the amazing thing. We know that regardless of how long our sequence is, this will never be more expensive than e over e minus 1 times the respective offline optimum for this particular instance. How do we get there? How do we now get to an integral solution? Well, we want to interpret these as probabilities. So what we kind of want to do is we want to buy the skis on the first day with probability 4/19. Then we want to buy the skis on the next day with, yes, some probability, so that the overall probability that we buy the skis within the first 2 days is 10/19. And we want to then make sure with these probabilities that we buy the skis within the first 3 days is 1. So more or less this is a probability distribution that we are defining this way. And as we will see in a second, as a matter of fact, the expected cost that we are incurring this way is no more than the fractional cost of our LP. Good. And how do we do this? So given any algorithm for the fractional problem, we define the following algorithm. What we do is we draw some theta uniformly at random from the interval 0 to 1, and then we will buy our skis as soon as the buy variable exceeds or is at least theta. And what we will show is that if the algorithm for the fractional problem is alpha competitive, then the above algorithm is a randomized alpha competitive algorithm for ski rental. How do we prove such a thing? Well, we introduce a random variable, zbuy, which will be the cost of buying the skis within the first M days. So we have M days overall, so we might as well just say, okay, this is the overall cost that we have for buying our skis. What is the probability of buying the skis within the first M days? Well, this is exactly true if within the first M days we reach a value of x buy which is at least theta, because this was what our algorithm said. We buy our skis as soon as x by t exceeds theta, or is at least theta to be precise. So this will be exactly x by m. Why that? Because theta was drawn from a uniform distribution. So we here have this is just something deterministic. This was coming from our deterministic algorithm. And we now just have the probability that theta, which is just which is a uniformly drawn random variable, that theta is at most something, and the probability for this is exactly this something. So what's the expectation of z bar? Well, this is exactly b times the probability that x bar is at least theta up to time m, which is then exactly equal to b times x by m. Then we also have x rent t, which we will define as the cost of renting the skis on the tth day. What is the probability of renting the skis on the tth day? Well, this is exactly the probability that x by m is smaller than x by t is smaller than theta. Why that? Because otherwise we're buying the skis. So if x by theta is at least x by t is at least theta, then we are buying the skis, or we have already bought the skis. But if we're still below theta, then we are renting the skis. Good. So what's that probability? This probability is exactly equal to 1 minus x by t. Good. Now, because of the constraint that x by t plus x rent t has to be at least 1, we now get that the probability that x by t is less than theta, that this is at most x rent t. As a matter of fact, in the algorithm that we devised, we set the rent variables to exactly this much. Now we're saying, okay, we're just using any algorithm for the fractional problem. This algorithm doesn't have to do this way. They only have to, whatever algorithm they are using, they have to set this the rent variable to at least this much. Because this is the constraint that we are enforcing. So this means that the probability that we're renting the skis, that our algorithm that we're devising now based on whatever fractional algorithm is given to us, that this algorithm is renting the skis is at most the value of this particular rent variable. So this means now that the expectation of z rent t is no more than x rent t t, and this also means that maybe this weird fractional algorithm is even increasing the rent variables later on. Okay, we even allow the algorithm to behave super weirdly, but they're certainly not allowed to decrease the rent variables. So this is why we can replace this t by an m here. Good. So what is now our overall cost? This is exactly the expectation of z bar plus the sum of these z rent t. So how much are we spending overall? Now what we'll do is we'll use linearity of expectation. And now we can use the bounds that we derived. The first thing we said, this is at most x by m, and the other things are at, okay, b times this much. The others are at most the sum of these rent variables. And so where are we? This is the eventual fractional cost of our fractional algorithm. And now we know that this is an alpha competitive algorithm. So we might say, replace this. This can only be, or this is upper bounded by alpha times the objective function value for any feasible fractional solution. And this, of course, is then at most alpha times c of opt of sigma, where we then say, okay, in this step we say this is, we could take as x star the optimal fractional solution, or even the optimal integral solution. Good. So this is already it. How does this work? Well, it is pretty straightforward because what we're doing here is we are we are kind of matching with our with this randomly drawn theta. We make sure that we buy the skis within the first t days with exactly the probability that the fractional algorithm is setting to the respective buy variable for the within the first t days. So what the fractional algorithm is kind of putting aside for buying the skis, this is the expected amount that we are paying. And this is already it. What I find interesting here is that we might have started right away designing this randomized algorithm, but I think it is conceptually easier to think about the fractional problem and only then to see, okay, the fractional problem and the randomized integral problem, they are effectively the same. We can interchange them. Good. For set cover, things aren't as simple. There, we will actually have to lose something because it is not true that for every fractional solution there is an integral solution of the same cost. This is true for the or at most this cost. This is true for ski rental, but this is not true for set cover, as we've actually already seen. So we'll have to be a little more careful there, but generally we will use now the same approach to also solve the set cover problem. Let's now talk about the problem of rounding fractional solutions for the fractional set cover problem to integral ones. And once again, we want to do this in an online way, so we have to kind of be aware that the fractions will change over time, and we want to make sure that at each point in time every element is covered. How do we do this? We want to now again interpret the fractions kind of as probabilities, but this will be a little more complicated now. So what we'll do is we won't just have one threshold, but we'll have a threshold for every set that we can use to cover. So more or less, we in the set cover example, in the ski rental example, we had just one threshold, namely for buying the skis, which is just one set, but we didn't have a threshold for every rent set, which are the singleton sets. Now we'll just have a threshold for each possible way of covering an element. And what our algorithm will now look like is as follows. So for every set S, we'll draw theta S from the uniform distribution on 0, 1. And upon arrival of the tth element or constraint, we will update, of course, the fractional variables according to an arbitrary fractional algorithm. And then we'll do the following. What we'll do is we will pick all sets S for which this x as t is at least 1 over 2 times ln t times theta s. And maybe let's first talk about what this first step means. So we now have a threshold for every set. Not only just one global threshold. Now one element or constraint arrives, we update our solution. We know how to do this. We even don't care how the algorithm does this. This is just some arbitrary algorithm. And then we hope that the following will cover the element if it is not already covered. It might even be that the element is already covered by what we did before. We don't really care. What we now do is we pick all sets S for which the respective fractional variable is at least 1 over 2 times ln t times theta s. Good. So this theta s, and this is the respective threshold for the set S. And if this set S now, if they are the fractional variable, now exceeds a scaled down version of the threshold, then we pick it. And what's this factor doing here? Well, this factor, you see, gets smaller and smaller the longer we proceed. Because initially it's even infinite. For t equals 1, it is infinite. But then for larger t, it gets smaller and smaller. This is actually what should be the main way of covering elements. But it might still be that our element is not covered. The element that has just arrived. For example, in the first step, this will not happen because, as I was saying, we have 1 over infinity here. No, we have 1 over 0 here, so infinity. So this will not be the case. So this is why we have a fallback, which is part B of this algorithm. And this now says if the element is still not covered, we choose one set S from the probability distribution defined by the x as t fractions. And for this, we have to note that these x as t, they sum up to at least 1. So, what's now this doing here? We are in the tth step, and hopefully our element is covered this way. But maybe it isn't. And then, what do we know? Well, we know that it is fractionally covered by these x as t. So their fractions sum up to 1. They sum up to at least 1, but for simplicity, let's assume that they sum up to exactly 1. They sum up to exactly 1, so this means we can interpret this as a probability distribution, and we can just draw one of the sets that is covering this element from exactly the probability distribution that we defined this way. And what we'll show is that we will lose an O of log m factor compared to the competitive ratio of the fractional algorithm that we're using here. So if the fractional algorithm is alpha competitive, the algorithm for the integral problem is O of alpha times log m competitive. Recall that m is the number of elements that we have in our universe. Last time we were talking about n, which is the number of sets that we can use to cover the elements. So what does this mean? In combination, we had last time an O of log n competitive algorithm for the fractional problem. If we plug this in here, then we get an O of log n times log m competitive algorithm for the which is integral, which gives us an integral solution for online set cover. Cool. So how do we prove this? What we'll do is we will first show that it is actually pretty unlikely that we go to this part B here. Initially it might be super likely, but the longer time goes on, the less likely it is that we are in this part, and the more likely it is that we are happy with what we're doing in part A. And this is exactly the first lemma that we prove. We will show that the probability that part B is executed in the T step is at most 1 over t squared. How do we prove such a thing? Well, recall that we execute this step if all the other things failed. So if whatever we did in step A, all of this did not cover the element. Well, something that might actually happen is that we before we at some point we ran into step B, and this way we covered an element, but let's ignore this. Let's only talk about we run into step B because step A wasn't sufficient so far. And to formalize this, we now use random variables capital X, where we say capital X is equal to 1 if S has been picked until around T because of case A, That is, this x as t is at least 1 over 2 times ln t times theta s. And otherwise, x as t is equal to 0. And what we will bound is the probability that for all sets S which contain element t, all of these x as t variables are 0. Good. And to do so, let's bound each of these probabilities of a 0 individually. And let's first consider the case that 2 times ln t times small x as t is at most 1. What's then the probability that x as t, capital X as t, is equal to 1? Well, this is exactly the probability that small x as t is at least 1 over 2 times ln t times theta s, or in other words, that the probability that theta s is at most 2 times ln t times x as t. And because this is a uniform distribution, we can say, okay, this is exactly equal to 2 times ln t times x as t. So this is true if these x as t are small enough. If they're small enough, then we can say, we certainly can say that this is the probability that this set has been chosen due to step A so far. Now we will bound this as follows. We will be using that 1 minus q is at most e to the negative q for any real numbers q. This, by the way, is an inequality that we've used at least once before, maybe even not more often. I'm losing track of this. We certainly use this when we analyze the fractional set cover algorithm, and this is something that as an inequality you will use very often. Good. So this now tells us that the probability that x as t is equal to 0, this probability is 1 minus 2 times ln t times x as t, of course. This will be at most e to the 2 times ln t times x as t. Good. Now there's also the other case that 2 times ln t times x as t is greater than 1. What do we do in this case? What's the probability that x as t is equal to 0? Well, when was it exactly? Under what circumstances did we pick this set? We chose it if x as t is at least this factor times the threshold. But this theta, this is always at most 1. So this thing here is fulfilled automatically, which means that the probability that we have not chosen the set is simply 0. And also here, we can use the same bound that we've just derived because this is a non-negative number. And now, as all these theta s are independent, we get that the probability that all of these capital X S t are 0 for all s which contain a certain t, this is equal to the product of the individual probabilities and this, each of these we can now bound using the formula that we've just derived, because this is true in any case, this upper bound. Now we can move the product inside the exponential function. And how big is this? This here, this will be at least 1 because we have this as a constraint. This element has to be covered. So all of this is at most e to the minus 2 times ln t. Or in other words, this is 1 over t squared. Good. So, how does this work? So far we showed that it is really, or the larger t gets, the less likely it becomes that an element is not covered by step A, although it was already covered by the fractional solution. Here we're using that it was already covered by the fractional solution, but still our randomized algorithm did not yet decide to cover it because the thresholds were too large, and this gets less and less likely over time. So over time it will happen that this step A takes care of almost everything, of covering almost all elements that we want to cover. So what we'll now do is we will see how expensive, how much are we spending for step A. And for this step A, we're now spending not much more than what the fractional solution is spending. And then we'll also talk about step B. How much are we spending for step B? So what we'll show is the following lemma. We'll show that the expected cost due to set S within the first m steps is at most and then we'll have 1 over the sum of all 1 over t squared, t going from 1 to m, plus 2 times ln m times cs times xs at time m. So, we are now first looking at only a single of our sets, and we ask, how expensive is it? How much is this set contributing to our cost? And we'll see, okay, this is only something in the order of log m times what it contributes to the fractional solution. Let's prove this. This is fortunately fairly easy, because what we'll do now is as follows. If we let xts be equal to 1, if s is chosen in part B of step t, then we'll have that the expectation and we will let xts be 0 otherwise. Now, what is the expectation of xts? This is exactly probability that xts is 1. And what is the probability that set S is chosen in part B of step T? Well, what has to happen for this? On the one hand, we'll have to end up in part B, and then also we'll have to choose this set. What's the probability that we end up in this part? It is 1 over t squared. This is what we've just shown in our lemma. And then we'll have probability that that this element is now chosen is at most small x s t. And those can only increase over time, so we can upper bound this by the fractional value at time m. So what is now the expected cost of S in the first m rounds? Well, we can write it as follows. This is technically speaking only an upper bound, because of course we can choose every set at most once. But we may now say, okay, how much is it contributing to us from the part B? And how much is it contributing for us to our cost from part A? And now we can just use linearity of expectation. how big are these things? Well, this expectation here we have already bounded. That's cool. So this is at most 1 over t squared times x as m. And what's the probability that this has been chosen due to part A? This is at most this much by just the thoughts that we've had also before. And if you now look at this, this already proves our lemma, because we have this factor times cs times x as m. This is exactly what we get here. Good. So we are almost there. To now bound the cost of our algorithm, we'll only have to add up all these terms. And this is done in the proof of our theorem. What do we have? What is the cost of our algorithm? This is what we also write as the expected cost of alg f sigma. This is, at most, take the sum over all sets, and for each of these sets, take the bound that we've just derived as to how much cost it how much cost we are spending on this set. Now, here this finite sum we can also bound by the infinite sum going up to infinity, and then this will be pi squared over 6. So this here is certainly at most something, some constant times 2 times ln m times, and then we'll have the sum of all cs times xs of m. And what do we know about this here? We know that this here is at most alpha times the cost of the optimal fractional solution. So overall what we're getting is this constant times 2 times ln m times alpha times, and then we can just take the optimal offline solution, the optimal integral offline solution, because this can be no better than the optimal fractional solution. And this proves our theorem. So maybe let's once again recap how we did this. We used this lemma, which is, I think, the important part, where we show that the cost that we are getting from each set is bounded by how much it is contributing to the fractional solution. And then we have Where did this come from? This came from this lemma. This lemma showed us that mostly we're using part A throughout our sequence. At the beginning, we might be using part B, but eventually the probability that a set is chosen due to part B, this is bounded by a constant times its fractional, its eventual fraction that it contributes to the fractional solution that we're computing online. And in combination, we then get to the point that this algorithm is actually alpha times log m competitive if the fractional algorithm is alpha competitive. And we don't actually care how this fractional algorithm works. We only need that it derives as a feasible fractional solution within a factor of alpha of the optimal fractional solution. Well, we even don't need this. It even would be fine if it was only within a factor of alpha of the optimal integral solution, which is something even weaker than this. Good. So now we have a full algorithm for the online set cover problem. And next, I want to tell you a little more about how we can extend the algorithm and the techniques that we used to also solve other problems. Good. We now have an algorithm for the online set cover problem, which uses multiple steps. Namely, it first solves the relaxation, and it does so by using the primal dual framework, and then it does randomized rounding on the solution. This is an approach, or these are general techniques which not only work for online set cover, but also for many other problems. And I'd now like to give you an idea how they also can work in other settings, or what other settings they also apply to. And the first thing is just a somewhat easy generalization of set cover, namely that we introduce arbitrary covering constraints. So our primal dual approach generalizes to LPs of the form minimize the sum of all Cj times Xj subject to sum of all Ai times Xj should be at least 1 for all I, and these Xj should be non-negative. Where all these Cj and Aij are non-negative, and we get to see one constraint at a time. And we may only increase variables. So this is more or less set cover, except for the fact that we are now allowing arbitrary coefficients alpha ij, or more precisely arbitrary non-negative coefficients alpha ai, aij here, which would be 0 or 1 in the set cover setting. And as a matter of fact, everything that we did in the last lecture regarding this primal dual algorithm, you can immediately also extend to this. There's not much you have to do. You actually, in our formula, you only have to include AiJ. The only reason why I didn't present it in this full generality was because I felt this was already complicated enough to understand only for set cover. But if you want to, you can also use it to solve this kind of LPs. At the same time, what we did today regarding the randomized rounding won't generalize. At least it won't generalize as we saw it today. You can in principle still use randomized rounding, but there you'll have to be a lot more careful, because what we did today was like saying, okay, with probability this and that, the element is not covered at all. Here now suddenly an integral solution might look different. An integral solution might not ask you to say, okay, one of these sets has to be picked, but rather it might even be that multiple of the xj have to be set to 1 for one of these constraints to be fulfilled. So this is why the getting to an integral solution is somewhat different, but obtaining a fractional solution online, you can do just the way we did this. Another extension is packing LPs. Or this is not exactly an extension, but it is a different perspective of what we did. Namely, recall the dual of our problem. This was to maximize the sum of the yi subject to the sum of the aij times yi is at most cj And in our problem, we had that these aij, they are either 0 or 1. And this is maybe having changed the notation a bit, but this is generally what the dual of the set cover LP looks like. Now, what can you do? You can actually use our algorithm for fractional set cover, and I hope you remember, it does not only give you a feasible primal solution, but also a dual solution, which is, if you scale it down, also feasible. And what can you do? Well, if you were now to solve such an LP online, where you're given one variable at a time, you could actually apply our algorithm. Namely, just do exactly what we were doing, but now your output will be the y's instead of the x's that were our output. Actually, more precisely, a scaled down version of the y's. And then we are getting the following. So one variable is revealed per step. And our algorithm will be O of log n competitive where n is the number of packing constraints. So what kind of problem can you use this for? Maybe let me give you one example. We might have a directed graph G and each edge E has capacity CE. And we are presented source sink pairs which I might want to call SKTK, and we may send flow from SK to TK when the pair is presented. Our goal is to maximize the overall flow. So let's maybe see what this can look like. In my graph here, I now have a couple of vertices. And many edges. All capacities are 1. And now, for example, the first request might be to 5, so we may not choose to send flow, for example, via this path. But then, this, for example, means if the second request, if we send a flow of 1, via top path, then the second request which would be 1, 4, for example, this would have to be rejected. Meaning that we couldn't send any flow along this path, whereas if we had sent flow along this bottom path, then we might still send flow along this top path. And for this problem, we can actually use our algorithm. Maybe let's quickly see how this works. Let's see what will be the fractional relaxation of this problem. Actually, I already stated this as a fractional problem now, So we would have to maximize sum of all k, sum of all p, f, k, p, subject to sum of all k and p, where E is in P, F, K, P is at most CE for all edges, E, and we'll have that the flow that we send along one path is no more than 1. So this is one way you could write this as an LP. We would now have, for every path, we would now have, for every path connecting SK to TK, we would now have a variable, how much flow we are sending along this path. Now, of course, for every edge, we have to maintain, or we have to make sure that we don't exceed the capacity, and also every path or every source sink pair may be for the overall flow that we're sending from that source to that sink may be no more than 1. I think I didn't mention this explicitly. Of course, you can also leave this out if you don't want this to happen, depending on your perspective on the actual problem, because maybe you want to eventually end up with an integral solution where you just connect sources and sinks via disjoint paths. Then you certainly would want this kind of a constraint. And in this case, our algorithm would now add these constraints one after the other, or add these variables one after the other, and run our fractional set cover algorithm, or, well, more importantly, consider the dual that is also produced by this. And then what are we getting? We will be getting an O of log number of edges plus number of requests competitive algorithm. Why that? Because the competitive ratio was log of the number of constraints that we have, and here we have, for every edge we have a constraint, and for every request, so every source sink pair, we have a constraint. Good. So this concludes our discussion of online set cover and also of the primal dual method for online algorithms. Although I'll have to say we are somewhat keep coming back to this primal dual perspective. Maybe it is not this explicitly, but throughout the semester it will remain important to, or it certainly never hurts to have this bit of an understanding of this primal dual perspective, although I don't think we will again use it this explicitly. Good. So I hope that you enjoyed today's lecture. Please reach out to me if you have any questions. See you next time. Stay safe. Bye.